Hello, Harper. It was really nice to see you over Thanksgiving. It was kind of crummy having to do all that social distancing stuff, but at least we got to be together. Maybe things will be a little better by Christmas. In this letter, we're going to look at the age of the Earth. Now, scientists tell us that the Earth is around 4.5 billion years old, but many people don't accept that. A lot of people read the first couple of chapters of Genesis and conclude that the entire universe and the Earth are only 6,000 years old. Well, as I write this in 2020, the Jewish calendar calls this year 5780. That is 5,780 years since creation. Well, obviously there's a very big difference in the two views. As I said earlier, God is the author of both nature and the Bible. And since there are no errors or contradictions with God, one of these assumptions about age is wrong. Well, I'll come back to that in a moment, but for now, we'll focus on why most geologists believe the Earth is very old. Our first video gives us a good overview of how the investigation has evolved over the centuries.
The Earth, our small rocky home floating in the vastness of space, is thought to be 4.54 billion years old, having formed nearly 10 billion years after the universe itself came to be in the Big Bang. But how can we, a species of organism which has existed for a mere 200,000 years, possibly have the intellect and evidence to have come to such a specific conclusion? It didn't happen overnight. The story of how we figured out the age of our planet is a long one, with many twists and turns, controversy, and debate. But this journey illustrates the amazing power of persistence and perseverance, and the true potential of the human mind. Nearly 2,400 years ago, Greek philosopher Aristotle theorized that the Earth was eternal, having existed forever. Many years later, during the 16th and 17th centuries, biblical references were analyzed and prominent theologians and philosophers suggested a drastically different estimate of 6,000 years. In fact, James Ussher, a 17th century Irish archbishop, took this a step further and declared definitively that the Earth had formed on Saturday, October 22nd, 4004 BC at 6 p.m. Just to be clear, there's no place in the Bible where an age of the Earth is offered. The estimate of 6,000 years suggested by Ussher and others is based entirely on the genealogical tables in the book of Genesis. Assuming they were a complete record, he deduced that 4,004 years had passed between the creation of the earth and the birth of Christ. With this began the ongoing debate between those who looked to science to come to an answer and those who relied solely on the Bible and its teachings. Around the same time that Ussher was analyzing the Bible to calculate an accurate age, naturalists like Nicholas Steno and William Smith were digging through a different kind of record, the rock record. Steno examined layers or strata within rock outcrops and the fossilized remains of living things found within those layers. He proposed that the deeper a layer, the older it is, an idea that would become known as superposition. He noted that the layers are originally laid down horizontally and that any strata that have been altered must have been exposed to forces at some point long after their original formation. Smith added that if widely separated layers contained the same fossils, those layers were likely the same age. Smith's nephew John Phillips later estimated an age of the Earth at nearly 100 million years, based largely on the work of Steno and Smith. At the same time, other scientists were making their own radical claims. This included naturalist Mikhail Lemonsnov, who suggested that Earth had been created entirely separate from the rest of the universe, and that this occurred several 100,000 years before the universe itself came into existence. For the first time, laboratory experiments were conducted to attempt to answer this seemingly unanswerable question: how old is the Earth? For example, in 1779, Georges Louis Leclerc created a small globe that resembled Earth in composition, and then he measured its rate of cooling. This led him to an estimated age of the Earth of 75,000 years. As you can see, there was a wide range of ideas about how old our planet actually is, well into the 1800s. It was at this point that geologists like Charles Lyell and James Hutton proposed further theories about the evolution of our planet. They specifically theorized that the changes that occurred on the planet were perpetual. Rocks were continuously forming, eroding away, and being redeposited. These ideas about how both gradual and rapid changes have been occurring on Earth throughout history eventually developed into an idea known as uniformitarianism, which suggests that understanding the past is the key to understanding the present. For example, if we observe limestone forming at the bottom of a warm, shallow sea today, we can infer that all limestone found on Earth likely formed in the very same way. While certainly important in our evolving understanding of geology, these ideas did not offer any further evidence or details about the Earth's actual age. In 1862, physicist William Thomson published calculations that suggested an age of the Earth at between 20 and 40 million years. This was based on the amount of time he felt it would take for a fully molten mass to cool to its current temperatures. Unfortunately, Thomson failed to acknowledge other factors which would impact how quickly the Earth cooled down, including things like radioactive decay and mantle convection. Shortly thereafter, around the end of the 19th century, John Jolly calculated the rate at which the oceans would have accumulated salt from the erosion of land materials, and he determined that the oceans must be between 80 and 100 million years old. Unfortunately, to many, these estimates seem far too low. Particularly Darwinian biologists who believed that the process of evolution that resulted in the varied and diverse life forms on Earth would have taken far longer to occur than was previously proposed. In the early 1900s, things changed drastically with the discovery of radioactivity. The amount of heat given off as naturally occurring radioactive isotopes decay would dramatically alter the rate at which the Earth would have cooled after its formation. The idea that this could have happened in a mere 100 million years now seemed impossible. But even more important than the implications for the rate of cooling was the realization that these radioactive isotopes decay not randomly, but at a predictable rate, in a process which now would become known as radioactive decay. Because it was predictable, scientists could determine the age of a rock based on the relative amounts of the radioactive elements that it contains. Discovered and confirmed by multiple scientists, including Ernest Rutherford, Frederick Soddy, and Bertram B. Boltwood in the early 20th century, radioactive decay and dating would become widely known as the key to our new understanding of the age of the Earth. This work, however, was not widely accepted at first, and as such, it did not progress until another scientist would revisit it. geologist Arthur Holmes used radioactive lead dating to estimate the age of several rock samples to be more than 1.6 billion years old, an estimate that was far older than had previously been suggested. Holmes later published The Age of the Earth, an Introduction to Geological Ideas, in which he presented an age range for the Earth of 1.6 to 3 billion years. Despite its promise, radioactive dating remained questionable in the eyes of the larger scientific community. It wasn't until 1956 that an age of 4.55 billion years, very close to today's accepted age, was determined by Claire Cameron Patterson, who used uranium-lead isotope dating on several meteorites. Meteorites are solid chunks of debris from an object like a comet, an asteroid, or a meteoroid. They originate in outer space and are able to survive the passage through the Earth's atmosphere, reaching the surface of the Earth. Now, this may sound confusing. Why would we look at meteorites which originate out in the solar system and not here on Earth to determine the age of the Earth? Well, it turns out that these meteorites offer a much more pure, unaltered sample than the rocks found here. Terrestrial rocks have undergone differentiation into the core and the mantle and the crust, and have then undergone a long history of mixing and unmixing by processes like plate tectonics and weathering, any or all of which may have adversely affected our ability to effectively date them. Meteorites represent the primitive material from which the original solar system was formed. The Earth is widely believed to have formed at the same time as the solar system, so dating the Earth and the solar system are one and the same. An estimated age of 4.54 billion years has since been confirmed dozens of times over, based on the analysis of hundreds of rock and meteorite samples collected on the surface of our planet. Additional confirmation has come from analysis of the rocks collected by the Apollo astronauts who explored the surface of the moon. That brings us to today, though it's not likely the end of the story. As with so many scientific mysteries, the question of the age of the Earth will never be unequivocally answered. We will continue to explore, developing more accurate methods for dating objects, uncovering more and more clues along the way. We can look forward to not only new answers, but most certainly new questions as well. Such is the nature of science.
Okay, our next video gives us a much clearer understanding of how radiometric dating works and why scientists believe it's reliable.
The carving of Mount Rushmore was completed in 1941, but the rocks it was carved into were completed quite a bit earlier than that, 1.7 billion years ago. How does a geologist know that? And how do they know that the Earth is 4.5 billion years old? The answer is a technique called radiometric dating, which lets us tell the age of certain types of rock. Radiometric dating relies on the fact that certain elements have what are called isotopes. These are versions of the atom with extra neutrons in them. Each radioactive isotope decays at a consistent rate. These measurements give us something called the half-life, or the amount of time it takes for 1/2 of the isotope to decay. When an isotope's half-life is up, half your original element will be gone, transformed into a different isotope. Another half-life and you're down to 1/4 of your original amount. A half-life after that and you're down to 1/8, and so on. The length of a half-life is different for every isotope. If you wait for enough half-lives to pass, you'll have a hard time detecting any of your original material. So to date something relatively recent, you want an isotope that decays quickly. To go older, you want an isotope that decays very slowly. The term carbon dating refers to dating using carbon-14, which we mentioned earlier. It has a half-life of 5,700 years, and most of it will be gone by about 50,000 years. To date things that are older than that, you want an isotope that decays very slowly. Uranium-238 has a half-life of 4.5 billion years. so it can be used to date things as old as the solar system itself. How do we use this to get the age of something? The unstable radioactive element that you use is called the parent, and the stable, happy isotope you end up with is called the daughter. Dating only works if the only source of the daughter isotope is the decay of the parent. You also need a rock that behaves a bit like a sealed time capsule, preventing daughter isotopes from leaving and keeping new parent isotopes from wandering in. That way, if you end up with half daughter and half parent isotopes, you know that one half-life has gone by, since the rock kept everything locked into the same place. Certain minerals form a tinker toy-like cage around any larger isotopes. This locks everything in place and makes for an excellent time capsule. Zircon crystals, for example, can trap atoms of radioactive uranium inside them, as well as its daughter isotope, lead. So, measure the proportion of uranium to lead in a zircon crystal, and you can figure out when it must have formed. Take this tiny zircon, for example, which would fit comfortably on the head of a pin. Believe it or not, this tiny zircon, which comes from Western Australia, is the oldest piece of Earth we've ever found. It's an absolutely mind-blowing 4.4 billion years old, and comes from when the Earth was only 150 million years after its formation. The zircon was dated using two different isotopes of uranium, uranium-235 and uranium-238. This provided a built-in cross-check, as you had two different clocks keeping time within the crystal. Whichever clock you look at, they give the same result. The uranium's been trapped in that zircon since it formed 4.4 billion years ago. Most dating techniques only work with certain types of rock. You can tell when lava erupted, for example, but can't figure out when sandstone formed. That's because the sandstone doesn't trap isotopes in the tinker toy-like cages that we mentioned earlier. Because there are other ways to tell how old things are in the world, we can compare those results with radiometric dating and show that they match. Trees, for example, put down a new ring each year they grow, and you can count backwards and figure out how old the tree is. You can also use carbon dating to figure out how old a particular ring on the tree is. Just like trees, ice in the Antarctic lays down a new layer each year, creating a similar ringed pattern. We can then compare that to the dates given by rocks trapped in the ice and show that they also match. If radiometric dating weren't reliable, we'd see differences between the results generated by it and those generated by these other methods. Fortunately, radiometric dating is reliable, which means if we go to Mount Rushmore, we know we can touch rocks that are 1.7 billion years old.
Radiometric dating as a technology had some problems in its infancy. Some volcanic rocks initially produced widely different results, casting doubt on the reliability of the technology. But as time passed, geologists learned that the problem was not the technology, but rather the choice of rocks to be measured. Today, this technology is considered very reliable. Geologists have learned what kinds of rocks are suited to this technology and which ones to avoid. Also, they're able to choose from several different isotopes that have different half-lives. When they run multiple tests with different isotopes and they come up with the same result, well, they're pretty sure they have the right answer. We also saw in the video that radiometric dating is not the only tool for estimating the age of things. Ice cores also provide useful information about age. We'll look at that dating method in a minute. Right now, I want to introduce you to a geologist, Dr. Ken Wohlgemuth. Dr. Ken Wohlgemuth holds a PhD in geochemistry from Columbia University. He worked 40 years as a petroleum geologist for Hess Corporation and was a member of the American Association of Petroleum Geologists. He's currently an adjunct professor of geosciences at the University of Tulsa. In this first video, he'll further explain radiometric dating.
Hello, I'm Jeff Zwerank, and I'm glad you've joined me today. I've also got in studio here with myself a good friend and colleague, Ken Wohlgemuth, is a geologist and has been working in the area of petroleum geology for more than 3 decades, and is also the founder of Solid Rock Lectures. And today we're going to ask the question, can you always trust radiometric dating? Ken, good to have you here today. This is one of those areas, again, as folks in the church talk about whether the earth is old or young, this is one of those areas that comes up of radiometric dating. And particularly, there was a group who studied radiometric dating, and one of their evidences that we couldn't trust it was that you get all of these discordant dates, or where you try and date things and you get dates that are different depending on what radiometric dating you use. So my question is, can you always trust radiometric dating?
Well, if we use the word always trust, the answer would be no, because there are examples where it doesn't work. So I will give you some examples back and forth. In general, the radiometric dating methods were developed between the 1930s and basically the 1950s. Mm-hmm. And they were established by understanding the radioactive decay of long half-life radioactive atoms.
So this is just the idea, get people
just the
idea that you've got this stuff that you have so much of it, and after so much time, half of it will decay. After that same amount of time, half of what's left will decay.
Correct.
This is what's been established and how we use it for a dating technique.
So in principle, a key component is that we can only date igneous rocks because of these methods. We can only date igneous rocks because it takes a rock that has been a lava and crystallizes down to a solid crystal, and it's the solid mineral crystals that will hold the radioactive parent atom in the crystal lattice when it decays to a daughter product.
Okay, so the idea of it being a magma is it's got to be able to mix and get new stuff in, but then it's got to crystallize so that what's in there doesn't go in and out, so you can keep track of the daughter and the parent molecule.
That is correct. And we refer to that time as setting the clock to zero.
Okay.
In other words, that's the starting time.
All right.
Now, some of the half-lives are so long that we cannot date these igneous rocks if they're really fresh and new, because it takes time for enough of the daughter product to be produced to measure it.
So the rulers, too. It's kind of like using a ruler to measure the width of a human hair or something. It just doesn't have the resolution you need.
That's exactly right.
Okay.
Or my wife's favorite example is you cannot use an oven thermometer to get the temperature of the baby who's sick.
That's a good point,
It just cannot work.
Right.
So there are examples that are put out there that claim it does not work, but oftentimes it's a misapplication of when this particular tool could be used. That's commonly what happens.
So one of the areas where with the radioactive dating, you have to be using it in the right range, or else you can't trust the dates that are coming out.
Perfectly said.
Okay.
I couldn't have said it better.
Okay.
So, for example, one well-known one is potassium argon. And potassium argon is the process has a 1.4 billion half-life for potassium-40.
Billion years, you mean?
Billion years
right,
for its half-life. So in short amounts of time, of just tens of thousands of years, or certainly tens and 20s of years, it needs at least something like 50,000 or 100,000 years of passage of time before we can even get a credible, trustworthy date with potassium argon.
Because you're not going to have enough daughter material to be able to measure it precisely enough.
Bingo.
Okay.
Right on. Exactly. So that's one factor. Another factor is we'll see a series of multiple applications of the 4 or 5 different radioactive atoms that are available, and they won't give exactly concordant ages. The question is this a problem with the individual methods? Well, one example scenario would be that it is not a problem with the area, it's the cooling time, in that the temperature times 0 was not set to 0 at the same time for all of those different systems within just, say, a few thousand years, when that rock may have cooled very, very slowly over a couple of millions of years or tens of millions of years, and therefore the different clocks basically locked in time 0 at different times. So that's one factor.
Okay.
The other factor is if the crystalline rock gets heated up enough long after it was first deposited and the timer was set to 0. Argon is a gas. So
Right.
potassium argon, that's a gas.
Right.
So argon, the argon atom then escapes out of the rock. So it gives an artificially incorrect young age, and we know about that.
So it sounds like when you do the dating properly, you can't just go and say, all right, let's measure X and let's measure Y, and therefore that gives us the date. You really have to be pretty diligent about, okay, where was this rock found? What was the environment?
Yeah.
You have to really be pretty careful about that, or else if you don't do that, you're going to be unsure of whether your date's
Exactly.
correct.
Now, are they often concordant ages? That is, they fit together? Yes, they certainly are. And one example, I'll give two examples. One example is a rock in Greenland, and I have a table that shows 4 different methods, and they all give the same answer within the error bars of that measurement of about 3.6 billion years. So that's one example.
Right.
The other example is even more dramatic. You're aware that an asteroid hit the Yucatan Peninsula in Mexico about the time of the demise of the dinosaurs.
Right.
That event was so catastrophic to the Earth that it melted lots of rock and it threw little spheres of molten rock up into the atmosphere.
Right.
And those spheres fell on Haiti, in North America, in Saskatchewan.
Big explosion.
Yeah,
to
it
say
was
nothing.
big. The science community has collected and measured those little glass spheres by different methods, and they have measured over 150 samples of the same event of material scattered over these thousands of miles. And I have a table that shows those 150 measured in 4 different laboratories by 3 different methods, and they all come out between 64 million years and 66 million years. That is just one of the most powerful, unbelievable concordance that demonstrates good credibility of radiometric dating methods.
Well, unless the decay rate of the isotopes has changed over time, it seems pretty convincing that the Earth is very old. As yet, no one has offered any verifiable evidence that the decay rates have changed. Now, I mentioned that ice cores are another completely independent means of measuring age. Ken will explain what has been found examining ice cores from Greenland.
Ken, it's good to have you here again. So, we look at how to date things. Tree rings are nice because you can count things, but we also have something similar with ice cores. So let's just kind of give us a little bit of background. How do we use ice cores to date things?
Okay. I consider tree rings as being the very simplest because anybody can count into the rings, okay? I consider ice cores the next to the simplest one in the sense that in this wintertime, snow falls on Greenland.
Right.
And in the summertime, that snow gets heated up by the sun and it forms a hoarfrost layer.
Okay.
So there's a difference of light and dark, that's a result of this process
So
of
very
summer,
similar
winter.
to the tree rings then.
Somewhat similar, but not as precise in
Right.
the sense as not as clear.
Right,
I mean,
okay.
tree rings are the best, no question about it.
Okay.
But the ice cores are a very different type of record. They're up on Greenland, and ice cores are in Antarctica. So,
Right.
so that's a big difference.
So what as we've used the ice cores, how many years can we count? How many layers can we count? What sorts of things have we found as we have analyzed these ice cores?
Okay. The scientific community in the 1990s, as I recall the time window, made a decision jointly between American scientists and Europeans to drill on Greenland up at the summit, right in the very middle of the highest, thickest range of the ice sheet in Greenland.
Why is that important to be in the middle?
That is where the maximum thickness will be,
Okay.
and out near the fringes, the ice is slowly flowing out toward the coast, so it is not stable.
Gotcha, okay.
And right
So
in the
it's a more
center,
reliable record.
It's
is
a
where
more
you're gonna find
reliable
it.
record.
Okay.
So the Europeans and the Americans separately drilled ice cores 2 miles from the ice surface of that ice sheet down to bedrock. So they have these two big long records.
Right.
The data shows that we can measure some properties of the water or the ice that's there that give us an indication when the end of the last ice age occurred, which was about 11,500 years ago.
Okay.
And since then, North America and the world has had basically a very uniform climate for the last 11,000 years.
Okay.
So that's number one.
All right.
Number two, how much passage of time? I was privileged to visit with Richard Alley, who's a professor at Penn State University, and he was active in this ice core research.
Okay.
He himself was up on that ice sheet for month after month after month, counting the layers as they brought the ice cores out, and they looked at them at the Quonset huts where they were doing the work up on the ice sheet.
Okay.
I asked him, how far back did you feel that you could count those layers with your eye before they got too thin? And he told me about 50,000 years.
50,000 years. That's a pretty long period of time.
That's a long time. That demonstrates that the Earth is at least well over 50,000 years.
And then presumably beyond that, just the weight of the ice is compressing the layers, or why do you have problems beyond that?
That's exactly correct. So deeper than that, ice under lots of pressure begins to flow.
Okay.
So there's an understanding that down below that 50,000 years, as the ice has gotten squeezed with the 1 mile thick of ice on top, the pressures are heavy, and slowly the ice layers are thinning
Right.
as the ice is slowly flowing out toward the coast.
Right, okay.
Okay? So in that process, for deeper than what they could see with the eye, they've also used electrodes because there are different chemical species that fall on the ice in the wintertime versus the summertime.
Right, okay.
So they use chemical species and electrodes to measure those differences to get timing on deeper than that.
So how far back, using the more sensitive techniques to see the layers, how far back can they push?
The estimate for Greenland is at about maybe 100,000 or 120,000.
Okay.
The challenge is down in bedrock.
Right.
There's a lot more uncertainty.
Right,
But
okay.
this is 100,000 years basically of a climate record that geologists have been able to discover. So it's a powerful piece of evidence observing the tail end and the nature of the temperature shifts back and forth during the last ice age.
So how would you respond to someone, and I've heard people argue that, well, we can't trust the ice cores to date because, we see these plains buried in wreckage that are a whole bunch of ice on top, and so clearly there weren't plains 40, 50,000 years ago, so this is not a reliable record.
Yeah. There is a record that is what's referred to as the Lost Squadron, where a group of airplanes that were flying during World War II could not land over in Europe, so they came back and they landed on the ice, very southern, southeastern edge of Greenland. So they were very close to the coast. So over a 50-year period, those planes were buried into about 250 feet of snow and ice with that extra every high snowfall that's along the coast. And the planes were also moved, I forget how much, it's a mile or two away from where they originally landed, as they were buried in the ice because of this flow of the ice. So that's not a location to get a reliable record long-term, and isn't directly related to the ice cores up on the summit.
Okay, let's talk for a moment about the big debate. Some very intelligent people have been studying the book of nature and concluded that the earth is very old. Other very intelligent people have been reading the Bible and concluded that the earth is very young. Obviously, they can't both be right. When I began to write these letters, I intended to focus exclusively on the science that convinced me that God does exist, that He designed this world and everything in it, and that the Bible is His revelation to mankind. So far, all we've looked at is cosmology and geology, and we've run into a pretty big question about the compatibility of science and the Bible. And naturally, that raises questions about the reliability of one or the other. So I think we need to address that question before we move on to physics. We'll hit the pause button on science for a moment and look at this issue in the next letter. Okay, that's it for now. I'm looking forward to seeing you over Christmas. Be careful driving home when the time comes. I love you, and I'll see you soon.